Hello, Honors Pre-Calculus. Today we're going to be covering lesson 7.5, Combinations and Permutations. Today we're going to be answering the question, how do you use combinations and permutations to solve counting problems? We're going to use the fundamental counting principle to solve counting problems and combinations and permutations. You should already know the idea of a factorial. Remember, that's the thing where, for example, if we have 5 factorial, it means 5 times 4 times 3 times 2 times 1. You take that positive integer and you multiply by every number from that number down to 1. And we also saw this thing called NCR in one of our previous lessons where we were talking about the binomial theorem. That is a combination. So if you remember the formula for that, that's what we're going to be using today for the combination portion. And then we also have to learn about permutations. We'll learn about the differences between all of those. And here's an example of something we'll be able to do by the end of the lesson. You are forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? And instead of you trying to kind of list through all of those options to figure out how many are possible, we can use some simple math with combinations and permutations to figure it out. All right, so that's where we're headed. Let's check out the beginning of the notes. All right, here we go. Lesson 7.5, combinations and permutations. Before we read any of this stuff at the top, let's just try example 1 so we can get a little bit of a preview of what's going on here. We're going to be selecting pairs of numbers at random. So here we go. Here's letter A. 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box, its number is written down, and the piece of paper is replaced in the box. Then a second piece of paper is drawn from the box and its number is written down. Finally, the two numbers are added together. How many different ways can a sum of 12 be obtained? Okay, so what's important to note here is that the piece of paper is replaced. So that's what we want to focus on. And for this example, we're just going to list out all the options. Okay, so let's say that we know we need a first number and a second number. And the biggest number in the box is 8. And 8 would have to be paired with a 4 in order to get a sum of 12. So the numbers 1, 2, and 3 can never be part of a sum of 2 numbers that sum to 12. So 4 is the smallest number that we can start with. And if we start by picking out a 4, we put the 4 back in the box. The second number that we draw is going to have to be an 8. If we start with a 5, the second number is going to have to be a 7. If we start with a 6, the second number is going to have to be a 6 again. And because we put the 6 back in the box, that's doable. If we start with a 7, the second number is going to have to be a 5. And if we start with an 8, the second number is going to have to be a 4. So that's a total of 1, 2, 3, 4, 5 different ways that a 12 could be obtained. So we have an answer of 5 ways. Let's look at letter B. 8 pieces of paper are numbered from 1 to 8 and placed in a box. Two pieces of paper are drawn from the box at the same time, and the numbers on the pieces of paper are written down and totaled. How many different ways can a sum of 12 be obtained? So this time, we're still going to kind of consider there being a first number and a second number. But since the piece of paper is not put back before the second paper is drawn, what can happen this time? So this time the first number could still be a 4, and then the second number could be an 8. The first number could be a 5, and the second number could be a 7. We can't have a 6 and then a 6 because there's only one number 6, and we didn't put the number back this time. So we have to skip that one. But we can just still do 7, 5, and 8, 4. So this time there's only 4 ways to obtain the sum. So the key thing that I want you to notice here, which is going to definitely be important throughout the lesson and especially next lesson, is that in part A, we would consider this to be with replacement. So when we pick the second number, the number that we picked the first time doesn't have any effect on what we're picking the second time because it's the same population that we're selecting from, right? It's the same sample. We still have all of the numbers from 1 to 8 by the time we get to the second number. In part B, not so fast, right? The second number is impacted by the first number because if we pick a 4, then for the second number, the 4 is gone. So now we only have 7, pieces of paper left to pick from. That's why we can't pick a 6 and then another 6. So we would say that this is without replacement. Okay. So then let's kind of go back up and take a look at the fundamental counting principle before we go into example 2. We've got 3 key vocab terms that we're going to be talking about this lesson: the fundamental counting principle, permutations, and combinations. We're going to start with the fundamental counting principle. Let E1 and E2 be 2 different events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. The number of ways that the 2 events can occur is M1 times M2. So that's a really fancy way of saying that if we are picking one thing from multiple groups of objects or items or whatever, then we can just multiply the totals together to get the total possibilities. So let's see what we mean in example 2. How many different pairs of letters from the English alphabet are possible? So pair, that means 2. So we are going to have 2 possible 2 letters that we're picking. And there are 26 letters in the alphabet. So the first option, the first letter has 26 options. And the second letter also has 26 options. The question did not tell us that we can't repeat a letter. So we could potentially repeat a letter. So that means there's 26 options for the first letter, 26 options for the second letter. So to find the total number of pairs, we will multiply 26 times 26 and get 676 pairs possible. Okay, let's use a similar thought for example 2b on the next page. Telephone numbers in the United States currently have 10 digits. The first 3 are the area code and the next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with a 0 or a 1. So we are looking for within each area code. So we're looking for the local telephone number. So it's going to be 7 digits long. And let's see, we have a local telephone number cannot begin with a 0 or a 1. So that means there are 8 remaining digits. The digits 2 through 9 could be in that first slot. But for every other digit, the digits are allowed to repeat. It could be any digit. So there are going to be 10 options for each one. And this is like a listing of how many options are possible for each digit. So to find the total, using the fundamental counting principle, we multiply all of these together. So it's going to be 8 times 10 times 10 times 10 times 10 times 10 times 10. And when we do that, we get 8 million different telephone numbers. So I'd be curious to know how this has impacted, the amount of area codes in the country, right? Because I'm imagining that originally people didn't have cell phones, so there would be like one landline phone number per family, per household. And now that everybody has their own cell phone and a lot of people still have landlines and people might have more than one number, people can have Google Voice numbers, et cetera. I'm wondering if, that's impacted area codes, that impacted how fast people may reach this 8 million total. I don't know. I don't know. That would be interesting to research. But let's move into example 3. In example 3, we want to know how many permutations are possible for the letters A, B, C, D, E, and F. And notice we have that word permutation. So let's go back and read the definition of a permutation. A permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. And I want you to note that permutations and combinations are very similar, but order is the key here. So in my permutation, order matters. In a combination, order doesn't matter. So for example, a permutation would be something like figure out how many ways you can put people in a certain order in line for something, or like you get first, second, and third place in an event, in a competition. Whereas a combination would be like pick a committee of 5 people, like on a committee of 5 people, it doesn't matter what order you picked those people in, they're all on the committee, right? So that's kind of one example of a difference here that we're talking about. So we've got some formulas. The number of permutations of n elements is, n factorial. There are n factorial different ways that n elements can be ordered. Number of permutations of n elements taken r at a time is npr, or n factorial over n minus r factorial. And we'll talk about distinguishable permutations in a minute. So let's take a look back at example 3 then. How many permutations are possible for the letters A, B, C, D, E, and F? So let's think this through. In the first position, any of those 6 letters can be first, right? Once we have that first letter selected, how many options are there for the second position? Well, we already used up one of the letters, so now there's only going to be 5 letters left. So it will be any of the 5 remaining letters. And that pattern is going to continue. So basically, we have 6 different letters. So if we write this out just like we did in the previous question, it'd be 1, 2, 3, 4, 5, 6. When the question says how many permutations, that means how many orderings of those letters are possible. We know there are 6 options for the first position. There's going to be 5 letters left by the time we get to the second position because we already used up one of the letters. Then there will be 4, and then 3, and then 2, and then finally there's only 1 letter left by the time we get to the last spot. So if we multiply all of these together, we're just getting 6 factorial, which is what the definition said for permutation. And so 6 factorial means that we have 720 possible permutations or orderings of those 6 letters. Now those that don't all form words, I don't know if any of them form words. I don't think so. That's not what the question asked. Just wanted to know how many ways can we order those 6 letters? And the answer is 720 different ways. Example 4, 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? Assume that there are no ties. Okay, so first, second, and third place. In that situation or scenario, order matters, right? Because if a horse comes in first place and a different horse comes in second place, and then they switch, that's a different way that the horses come in first, second, and third. So order matters here, so we're doing a permutation. If we look at the first position, there are 8 different horses, so there's 8 options for horses that could come in first. If we look at the second position, there are going to be 7 horses left that could come in second after the first horse finished. And if we look at third place, there are 6 horses left after the first 2 horses finished. So we got 8 options and then 7 remaining options. And then 6 remaining options. So if we use the fundamental counting principle, it'll be 8 times 7 times 6, or 336 different ways. And we could also use the permutation formula to figure this out. So we could do 8p3, which is coming straight from the front of the notes. The formula is 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. If we write that all out to simplify it, we would end up with 8 times 7 times 6 times 5 factorial over 5 factorial, so that the 5 factorials could cancel and leave us with 8 times 7 times 6, which we know from the line right above is 336. So we got the same answer multiple ways. In this question, it wasn't too bad to just think it through using the fundamental counting principle, but the permutation formula will always work as well. You can also use a calculator here. Where is my calculator? Here it is. We can do this on the calculator. If you type in the 8 first, then you go to math, probability, number 2 is NPR, then we type in 3, we get the same answer, 336, the calculator does it for us. Okay, all right, example 5, distinguishable permutations. So now we're gonna be using that next section within permutations from the front. Suppose that a set of n objects has n1 of one kind of object, n2 of a second kind, and so on. And the total number of objects are split into these like groupings. The number of distinguishable permutations of n objects is like this. So let me show you what I mean. How many distinguishable ways can the letters in B-A-N-A-N-A be written? Banana. So what I mean by distinguishable is if we switch these two n's right now, it still is the word banana and it didn't change anything. The n's are the same as each other. So if we switch the order of the n's, it's not like we have a new word or a new pattern, right? It's not distinguishable from the original. So we don't want to include just switching the spot of the two n's or switching any of the a's in our list of distinguishable permutations. So first I'm going to figure out how many different types of items are there. There's 3. There's B's, there's A's, and there's N's. There's only 1 B. There are 3 A's, and there are 2 N's. So if we follow the formula from the front, there are 6 total items. So we have 6 factorial on the top, and then we do each of the groupings factorial on the bottom. So it's 1 factorial times 3 factorial times 2 factorial. So we do 6 times 5 times 4 times 3 times 2 times 1 on top, and then 1 times 3 times 2 times 1 times 2 times 1 on the bottom. That's dividing out all of the, permutations from the top where the A's or the N's are just switched around. So that's a total of 60 distinguishable permutations. All right, let's keep going. Example 6, combinations of n elements taken r at a time. In how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? This time it says the order of the 3 letters is not important. The order is not important. And even in the title, for example 6, it says combinations. So now we're looking at our last new vocab term, combinations. A combination is a method of selecting a subset of a larger set in which order is not important. The number of combinations of n elements taken r at a time is NCR equals n factorial over n minus r factorial times r factorial. That formula we used in the binomial theorem lesson. We called it NCR, but now we're going to look at it as its own thing, as a combination, very similar to permutation, but order doesn't matter. Okay. So we are picking 3 letters, and the order doesn't matter. Well, if we just use the formula, there are 5 options, and we're choosing 3 of them. So you always put the bigger number first as the n, and the smaller number, the number that we're selecting, is the r. In the formula, that makes it 5 factorial over 2 factorial times 3 factorial, which equals 10. Okay, we could type that in. We could calculate this by hand. We could also use the calculator, just like we did in the last one. We could type in a 5, math, probability number 3, and we get 10. Okay, so that's how we do that. So there's 10 different ways. But I want to see if we can list these out. So let's see if we can. So we have A, B, C. And that takes care of all of the combinations that include the A, the B, and the C. So A, C, B, B, A, C, C, B, A. None of those are different from this one, right? The order is not important, it says. So A, B, and C, we picked A, B, and C. That is all of the ones that have the A, the B, and the C. Okay, so then let's see if we can list all of the combinations that have A and a B. So it would be A, B, and D, A, B, and E. Okay, so there were only 3. So now let's see if we do A and C. We already have AC paired with B. So we need AC paired with D and AC paired with E. We already have A and D paired with B and A and D paired with C. So we need A and D paired with E. And that's all of the combinations that have an A in them. So now let's go to the B. We don't need to go backwards to the A. We have every combination that had A in it already. So we need B, C, D, and B, C, E. And then we need B, D, E. And the only one left that doesn't have an A or a B in it is going to be C, D, E. And we got 10. So there, we just proved that that formula worked. There are all of the options. All right, let's check out example 7. A standard poker hand consists of 5 cards dealt from a deck of 52 cards. How many different poker hands are possible? After the cards are dealt, the player may reorder them, so order is not important. So there are 52 cards in a deck of cards. Here they are. How many different hands are possible? So we're picking 5, and it says order doesn't matter, so we're going to use a combination. So if we wanted to do this by hand, we would do 52 factorial over 52 minus 5 factorial times 5 factorial, which is 52 factorial over 47 factorial 5 factorial, which you could figure out in your calculator, or you could just type this into your calculator. You're going to end up with 2,598,960 different poker hands, which is a crazy high number, which is why poker can be very interesting, right? Because there's so many different things that might happen. Example 8, forming a team. You are forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? This is going to be a combination of combinations and the fundamental counting principle. So let's focus just on the girls first. We have to pick 5 girls out of a set of 10 girls. How are we going to do that? The order that we pick the girls does not matter, right? It just asks how many different teams are possible. So we're going to have 10 total girls, and we're choosing 5 of them. So if I do that on the calculator, I get 252. For the boys, there are 15 different boys, and we're picking 7 of them. So I do that on the calculator, I end up with 6,435 different sets of boys that I could pick. And for the total, for every one of these 252 options for the set of 5 girls, they could be paired with all 6,435 sets of 7 boys, and that would be a different team, right? So we're going to have 252 times 6,435. So we get 1,621,620 different swim teams. And that's how you do it. All right, so now you know everything there is to know about the fundamental counting principle, combinations, and permutations. Please let me know if you have any questions, and have a good day. Thanks.